So yeah, good morning, everyone. So getting started today, I want to explain convergence of technology and music, that being neural DSP, and how they are redefining how we capture and reproduce rich analog tones of guitar amplifiers using deep learning. So let's dive into how the technology works, how it's trained, and a little bit of why it's changing the game for guitarists. So Neural DSP is a Finnish company known for its high fidelity amplifier plugins and quad cortex, big words, but yeah, which is their signature hardware floor unit. And their goal is to digitally recreate analog gear. So these are your amps, cabinets, and pedals with a precision that even trained musicians cannot tell the difference. But at the core, they're not just using traditional signal processing. Their products use neural network-based modeling, hence the name Neural DSP. Yeah. Traditionally, guitarists have relied on analog equipment. This is inclusive of amps, cabinets, pedals, vacuum tubes, diodes, transistors, etc. All these things to create their sound. And these devices are beloved for their nonlinear behavior, their saturation, and just the way they respond to a player's touch. But an analog gear is often bulky, it's expensive, and it can be fragile. So with the music production moving towards digital platforms, there's obviously a growing demand for software that can simply replicate these analog tones. This process is known as virtual analog modeling, and it comes in two types. There's white box modeling and black box modeling. So white box models simulate the actual circuits. They're accurate but computationally heavy. And in contrast, black box models don't simulate the circuitry. They learn how the system behaves from input and output data. So analog gear is nonlinear, dynamic, and time-dependent. The traditional modeling techniques like component modeling or convolution-based impulse responses often fall short when trying to replicate the subtleties of analog saturation or feedback loops or attack response. However, deep learning, specifically deep neural networks, can learn these complex behaviors end-to-end by observing the input and output signal pairs without needing to explicitly model every resistor, capacitor, or diode. So what is the architecture behind the sound? So Neural DSP employs deep convolutional neural networks or WaveNet-inspired architectures to process raw audio directly. So these models take in a time domain guitar signal, which is the dry direct input track, and generate a processed output that matches the tone and dynamics of a target amplifier. Some of the key traits are the dilated causal convolutions, specifically stacked dilated convolutions, which enable networks to have very large receptive fields with just a few layers. And it does this while preserving the input resolution throughout the network and being computationally efficient. Then there's residual and skip connections. The use of residual and skip block and skip channels is inspired by pixel CNN architecture, and that was for images. Both residual and parameterized skip connections are used throughout the network to speed up convergence and enable training of much deeper models. Then obviously there's real-time inference optimization, and this gives the power for it to be suitable for live performance because of how they were able to minimize the latency. So the model is able to make predictions on demand. So how is the model actually trained? Obviously, there's a big plethora of data collection. They send thousands of direct input guitar samples through the real amp setup, and simultaneously they record both the dry input and mic'd output signal. Then it goes to pre-processing, where the signals are normalized and segmented into manageable frames. And then there's evaluated. So the training objectives will use loss functions that minimize the difference between the model's predicted output and the real amp's output. So some of the common loss functions that they use are mean squared error in the time domain, simply quantifying the average squared difference between predicted and actual values over a period of time. Another example is multi-scale spectral losses in the frequency domain, and it's simplified. It just compares and evaluates the similarity between signals. Some of the models use perceptual loss, which compares audio more like human hearing would, and it aims to improve the audio quality in the models by aligning it with human perception rather than solely relying on mathematically driven loss functions. So and for all this training, the infrastructure needed is high performance GPUs, and it takes over days or weeks. And then once trained, the they export the model to a lightweight format for real-time use in plugins and hardware. So yeah, where is the real-time execution happening? So once these models are trained and exported, they run in two places. One is plugins, and these are used in digital audio workstations like Logic or Cubase, with the neural model running efficiently on CPU or GPU in near real time. It's around 3 milliseconds of latency. And the other place is the quad cortex, which is a floorboard with a dedicated DSP chip. The model is compiled and quantized for low power and low latency use. A really cool feature of the quad cortex is something called neural capture, and it allows users to actually train models on their own gear by feeding it dry and wet signals. So yeah, some advantages over traditional modeling, like why it's actually a game changer, is it's accurate with its ability to capture the nuances of analog gear. And this includes harmonic distortion, sag, and feedback behavior. It is efficient with trained models light enough for live use. It is scalable for neural DSP with the ability to add new amps by just feeding in more data and retraining. And lastly, it adds a touch of personalization with neural capture, letting musicians model their own setups. However, it's not without challenges. The training quality depends heavily on data quality and diversity. Real-time performance requires significant and constant optimization and pruning. And obviously, no model is perfect. There's always going to be a trade-off between realism and latency or CPU load. And yeah, in closing, hopefully this just shows how neural DSP is utilizing machine learning to elevate an old school craft. And as musicians like demand more flexibility and tone accuracy, and importantly, without dragging along a 30 kilogram amp setup, solutions like these are reshaping the future of digital audio and how we capture sound. Yeah, thank you. I wanted to play a 15-second video of just how it runs in real time. So hope you guys enjoy. Ooh, yeah, thank you.